something sits at the edge of the observable universe that should not be there. A galaxy, fully formed, massive, ancient in all the wrong ways. And the James Webb Space Telescope stared right at it, just 1 billion years after the Big Bang. Every model we built said that was impossible. Galaxies need time, billions of years of time. Gravity pulling, stars exploding, matter colliding. Webb found one that skipped all of that. We are going to walk through 33 discoveries that are quietly dismantling the story we told about how everything began. Mature galaxies at cosmic dawn, black holes that grew too fast, structures that had no time to exist. If you enjoy what we build here, like and subscribe. It helps more than you know. Prepare yourselves. We begin. The James Webb Space Telescope opened its golden eye in the summer of 2010, and within weeks, scientists were quietly panicking. Not loudly. Cosmologists do not panic loudly. They send careful emails with phrases like inconsistent with predictions and requires further investigation. But behind those measured words, something extraordinary was happening. The telescope built to confirm what we already believed was instead pulling apart the story we had spent decades constructing. To understand why, you need to know what Webb was supposed to do. For 30 years, the Hubble Space Telescope gave us our deepest views of the universe. It showed us galaxies billions of light years away, ancient and dim, small and chaotic. Those images matched our models beautifully. The early universe looked young because it was young. Galaxies were scrappy, irregular, still figuring themselves out. Everything made sense. Webb was designed to go further. Deeper in space means further back in time, because light takes time to travel. When you look at something 10 billion light years away, you are seeing light that left 10 billion years ago. Webb's infrared vision was built to pierce through the dust and distance that Hubble could not, reaching back toward the very first billion years of cosmic history. Scientists had predictions ready. They expected to find the earliest galaxies looking primitive, small, clumpy, unorganized, the cosmic equivalent of rough sketches before the painting. Webb found the painting, fully finished, framed, hanging on a wall that the timeline said had not been built yet. The first deep field images came back, and researchers started flagging objects that their models could not place. Galaxies with the mass of our own Milky Way, appearing in a universe that was only a fraction of its current age. Structures with organized shapes, brightness levels that implied enormous numbers of stars, already burning, already dying, already enriching the space around them with the heavy elements that stars take billions of years to forge. One team looked at their results and wrote in a published paper that these galaxies were too massive, too early. Another researcher said openly that if the observations held up, and they did hold up, then something in our foundational model of how the universe evolves was broken. Here is what makes that so striking. The standard model of cosmology, called lambda cold dark matter, had survived every test thrown at it for decades. It correctly predicted the large-scale structure of the universe, the temperature patterns in the oldest light we can detect, the way galaxies cluster across billions of light years. It was one of the most successful scientific models ever built. Physicists trusted it the way engineers trust gravity. Webb did not chip away at it. Webb walked up and pulled a load-bearing wall. Now, confirmed discoveries require careful verification. Multiple teams cross-checking the same data. Redshift measurements locked down. Alternative explanations ruled out one by one. That process took time. But as it completed, the results did not soften. They sharpened. The galaxies were real. The timeline was real. The problem was real. And the deeper Webb looked, the more of them appeared. Hundreds of candidates, dozens confirmed. Each one sitting in an era of the universe where, according to everything we calculated, it had no right to exist. You are standing at the beginning of a story that cosmology is still writing in real time. The telescope meant to answer our oldest questions handed us a list of new ones instead. The first question on that list: what exactly did we get wrong about how galaxies are born? For 50 years, one story held the universe together. It started with the Big Bang, around 13.8 billion years ago, a single point of unimaginable density and heat, expanding outward in every direction. Within the first few minutes, hydrogen and helium formed. The universe cooled, darkness fell across everything. Then slowly, gravity went to work. The early universe was almost perfectly smooth. Almost. There were tiny variations in density, ripples so small they measured just 1 part in 100,000. But those ripples were enough. Gravity pulled hydrogen gas toward the slightly denser regions. Over hundreds of millions of years, the gas compressed. It heated, eventually it ignited, and the first stars burned to life. Those stars lived fast and died violently, scattering heavier elements across space. New clouds of gas, now seeded with carbon and oxygen and iron, collapsed into the next generation of stars. Those stars gathered into clusters. Clusters merged into galaxies. Galaxies pulled together into groups, then clusters, then the vast cosmic web of filaments and voids we see today. This process, called hierarchical structure formation, was elegant. It matched observations beautifully. Small things form first, then merge into bigger things over time. Simple, logical, supported by decades of data. The model had a name: lambda, cold, dark matter. Lambda referred to dark energy, the mysterious force driving the universe's accelerating expansion. Cold, dark matter referred to the invisible scaffolding of matter that does not emit light, but does exert gravity, acting as the skeleton around which normal matter clusters. Together, these two invisible ingredients made up roughly 95% of everything. Normal matter, the stuff we can see and touch, was a thin layer of foam on top of a deep, dark ocean. The model said that was fine. It still explained everything we could measure. And it did, spectacularly. Scientists used it to predict the precise pattern of temperature fluctuations in the cosmic microwave background, the faint glow of light left over from the early universe. Those predictions matched measurements to extraordinary precision. The model predicted how many galaxy clusters should exist at various distances. Matched, it predicted the distribution of hydrogen gas across billions of light years. Matched again. By the time Webb launched, lambda cold dark matter was so well tested that most cosmologists treated it as settled science. The remaining work, they thought, was filling in details. There was one assumption buried inside the model that almost nobody questioned. Galaxy formation takes time. A lot of it. Building a massive structured galaxy requires gas to collapse, stars to form, those stars to die and seed new generations, and all of that cycling through multiple rounds across hundreds of millions to billions of years. The model was precise about this. In the first 500 million years after the Big Bang, you might find small, chaotic, proto-galaxies just beginning to pull themselves together. Massive, chemically rich, well-organized galaxies belonged much later in the timeline. That was not a loose prediction. It was a specific testable claim built into the mathematics of how matter behaves under gravity. Webb tested it, and somewhere in the infrared light of the deep universe, that claim started to crack. The next images coming down from Webb would force researchers to ask a question they had not seriously entertained before. What if the early universe was not calm and gradual at all? What if something accelerated the whole process in ways the model never accounted for? The answer to that question was stranger than anyone expected. Picture a crime scene where the body is older than the building it was found in. That is roughly the situation astronomers faced when Webb's first deep field images finished processing. Buried in a patch of sky smaller than a grain of sand, held at arm's length, they found a galaxy glowing with the light of hundreds of billions of stars. Massive, structured, chemically complex, and sitting at a point in time when the universe was less than 500 million years old. This specific object, confirmed and studied by multiple independent teams, carries the catalog designation JADES GS Zone 4.0. Scientists measured its redshift precisely, which is the stretching of its light caused by the expansion of the universe, and that measurement placed it at a record-breaking distance. The light we see from it left when the cosmos was roughly 300 million years old. To feel what that means, consider this. The universe is 13.8 billion years old. 300 million years is about 2% of that total age. Imagine the entire history of the universe compressed into a single day. This galaxy existed before the clock hit 30 minutes, and it already had a mass greater than 600 million times the mass of our own star, already burning stars at a rate that would take our entire galaxy and multiply its output by several times. Teams ran the numbers, then ran them again. The galaxy's brightness told them how many stars it contained. Its color told them how old those stars were. Its chemical signature told them that multiple generations of massive stars had already lived, burned out, and died inside it, seeding the galaxy with oxygen and other heavy elements. Multiple generations of stars. In 300 million years, our best models said that process alone should take at least 1 billion years, possibly 2. Here is where the story sharpens. Every explanation scientists tried to offer ran into the same wall. Could it be a statistical fluke? One rare object that happened to form faster than average? Possibly, if there was one. But Webb kept finding more. Not dozens. Hundreds of candidates at similar or even earlier epochs, with similar levels of mass and chemical development. The statistical argument collapsed. One anomaly is a surprise. Hundreds of anomalies is a pattern, and a pattern means the model is missing something. One researcher described the feeling in the field as similar to discovering that a marathon runner finished the race before the starting gun was fired. The evidence for their arrival is right there. The clock says it cannot be real. Yet, there they stand. What made this find even more destabilizing was its size. The galaxy spans roughly 1,600 light-years across, which is physically large for its era. Early universe galaxies, according to the standard model, should be compact, cramped, barely holding together. This one was already stretching itself out across space, with the confidence of something that had been around for a long time. The Webb team published their findings. The broader community scrutinized the data hard. Alternative explanations were proposed and tested. Contamination of the signal by other objects? Ruled out. Calibration errors in the telescope? Checked and cleared. Misidentified redshift? Confirmed through multiple spectroscopic measurements. The galaxy was real. Its age was real. Its mass was real. Something had turbocharged structure formation in the early universe. Something the model had never accounted for. And whatever that something was, it had left its fingerprints all over the first chapter of cosmic history. The question burning through astrophysics labs around the world was simple. How does a galaxy build itself that fast? Building a galaxy from scratch sounds dramatic. The reality is mostly waiting. Gravity pulls clouds of hydrogen gas together. Those clouds compress under their own weight until the pressure and heat at the center cross a threshold and hydrogen atoms start fusing into helium. A star ignites. That process, from diffuse cloud to burning star, takes millions of years on its own. Then you need millions of those stars. Then those stars need to live, generate energy, produce heavier elements in their cores, and eventually die in explosions that scatter those elements into space. Then the next generation of stars forms from that enriched material, and the next. Each cycle takes hundreds of millions of years. After enough cycles, you have a galaxy with structure, with chemical complexity, with a coherent rotating disk, or an elliptical shape built through mergers and the slow gravitational dance of billions of objects. The timescale built into our models for producing a galaxy like the Milky Way, with its mass, its chemical richness, its organized spiral arms, runs to several billion years minimum. That is the physics. Stars are not fast. Gravity is patient. Chemistry accumulates slowly. So when Webb found galaxies displaying all of that complexity inside the first 500 million years, the first instinct of every physicist was to ask what the numbers were actually measuring. Could the brightness be misleading? In some cases, a very active black hole at a galaxy's center can flood the surrounding region with light, making the galaxy look more massive and star-rich than it truly is. Teams checked for this. Some early candidates were indeed contaminated by central black hole activity. Those got removed from the sample. The remaining galaxies held. Their brightness matched star populations, confirmed through spectroscopy, the technique of splitting light into its component wavelengths to read the chemical fingerprints of what produced it. Spectroscopy does not lie. It reads the actual atoms doing the glowing. Those atoms told a consistent story. Stars, in enormous numbers burning at full power, in a universe barely past its infancy. Now here is the deeper problem that this creates. Stars form from gas. The early universe had plenty of hydrogen and helium, the raw fuel. But for galaxies to grow this massive, this fast, the gas needed to collapse into stars at rates far beyond anything in the modern universe. Today, our galaxy produces roughly a few new stars per year. These early galaxies were producing them at rates equivalent to thousands per year, sustained over hundreds of millions of years. Think of the difference between filling a bathtub with a faucet dripping once per second versus turning on every tap in the building at once. The early universe, according to Webb, had all the taps running. The standard model allowed for faster star formation in the early universe. Denser gas, more available fuel, higher collision rates. But the models predicted a factor of a few times faster. Webb found a factor of hundreds. The gap between prediction and observation is too wide to paper over with minor adjustments. Something was pushing star formation into overdrive. Something was collapsing gas faster than gravity alone should have managed. And something was keeping those galaxies from flying apart as they grew at breakneck speed. That something might have lived at the very beginning of everything, in an era so extreme we have no direct way to observe it. But Webb found clues pointing straight toward it. There was a time when the universe was completely dark. After the Big Bang, the early universe glowed with ferocious heat and light. Then it cooled. The electrons and protons that had been zipping freely through that hot plasma combined into neutral hydrogen atoms, and the universe became transparent. Light could travel freely for the first time. That light still reaches us today as the cosmic microwave background, and it is the oldest thing we can directly detect. But after that moment of clarity, darkness fell. The hydrogen gas spread out across space, cool and neutral, blocking most forms of radiation. Stars had not yet formed in significant numbers. Galaxies had not organized themselves yet. The universe entered what astronomers call the cosmic dark ages, a period of perhaps several 100 million years, where nothing visible was happening. Then the first stars switched on. Their ultraviolet radiation began punching holes in the surrounding hydrogen fog, ionizing it, turning neutral atoms back into free electrons and protons. Over time, those ionized bubbles grew and merged until the entire universe was transparent again. This process is called reionization, and it marks the end of the cosmic dark ages and the beginning of the cosmic dawn. Our models predicted reionization was a gradual process. It began around 400 million years after the Big Bang and finished somewhere around 1 billion years in. The first galaxies were faint and few, slowly chipping away at the hydrogen fog, like sunlight gradually burning through morning mist. Webb looked directly at that era and found something different. The reionization process appears to have run faster and started earlier than the models predicted. Instead of a slow fade from dark to light, Webb's observations suggest it happened in a more dramatic burst, driven by a population of early galaxies more numerous and more luminous than anyone expected. The evidence comes from multiple directions. Webb detected galaxies producing ultraviolet radiation at rates that, when totaled across the early galaxy population, exceeded what the standard model projected by a significant margin. Enough excess radiation to explain a faster reionization timeline. And here is the part that reframes everything. If reionization happened faster, that means more galaxies were active earlier, which means structure formation was further along at an earlier date than the models allowed, which circles back to the core problem. The early universe was organized, lit up, and producing complex chemistry on a schedule that our theoretical framework cannot account for. One image from Webb captured a line of sight through the early universe, where the hydrogen fog was already clearing at a time the model said it should still be fully opaque. The timing was off by hundreds of millions of years. Scientists confirmed this through measurements of the spectra of distant quasars, which are brilliant galactic cores whose light passes through the intervening hydrogen. The way that light gets absorbed reveals how much neutral hydrogen is present along the path. The absorption pattern Webb measured pointed to a universe that cleared its fog ahead of schedule. What cleared it so fast? Early galaxies forming stars at furious rates, pumping out radiation in volumes the model never predicted. Which brings us back to the same question dressed in new clothes. How were those galaxies already so powerful? The answer may start with the very first generation of stars. Stars so extreme that nothing like them exists anywhere in the universe today. And they may have changed everything. Every object in the universe is moving away from every other object, carried by the expansion of space itself. And that expansion does something measurable to light. When a source of light moves away from you, the light waves stretch out. They shift toward the red end of the spectrum. The faster the recession, the greater the stretching. Astronomers call this redshift, and it works as a precise cosmic ruler, connecting the color of a galaxy's light to its distance, and therefore to its age. A galaxy with a redshift of 1 sits about 8 billion light-years away. Its light shows us how it looked 8 billion years ago. A galaxy with a redshift of 10 sits so far away that its light shows us the universe as it was when only about 500 million years had passed since the Big Bang. The galaxy Webb confirmed at record distance carried a redshift of 14.32. When its light left, the universe was 300 million years old. To measure redshift, you need spectroscopy. You split the galaxy's light into its individual wavelengths and look for known chemical signatures, specific patterns of absorption or emission left by hydrogen, oxygen, carbon, and other elements. Those patterns are like fingerprints. You know exactly where they should appear in the spectrum for a stationary source. If they appear shifted toward longer wavelengths, you measure by how much, and that measurement tells you the redshift precisely. Before Webb, measuring the redshift of extremely distant galaxies was brutally difficult. The Hubble Space Telescope worked primarily in visible and ultraviolet light. But a galaxy at redshift 10 has had its visible light stretched so far into the infrared that Hubble could only detect it faintly and could not always get the spectroscopic detail needed for a clean measurement. Many early galaxy candidates discovered by Hubble had redshift estimates that turned out to be wrong when better instruments checked them. Webb changed this completely. Its instruments are optimized for infrared light, exactly the wavelength range where distant galaxy light lands after being stretched by cosmic expansion. Webb can take a spectrum of a galaxy at redshift 14 with more clarity than Hubble could manage for a galaxy at redshift 4. This matters enormously for the current scientific crisis. Earlier claims about impossible early galaxies were sometimes dismissed by saying the redshift estimates were unreliable. Webb's spectroscopic confirmations removed that escape route. The measurements are tight, the uncertainties are small. The galaxies are where Webb says they are. The confirmed record holder carries a confirmed oxygen emission line in its spectrum. Oxygen, a heavy element that stars must produce through nuclear fusion and then scatter into space when they die. Finding oxygen in a galaxy 300 million years after the Big Bang means multiple generations of massive stars had already lived and died inside it. The chemical clock that oxygen represents ticks over billions of years in our current models. Webb found it running centuries ahead of schedule, and this single measurement, oxygen at redshift 14, became one of the clearest signals in the data that something fundamental about our timeline of the early universe needed revision. The chemistry was too rich. The galaxy was too old in all the ways that matter. The light was telling a story the model had no chapter for. What kind of star could have seeded a galaxy with oxygen in just a few 100 million years? That answer requires traveling back to the very beginning of stellar history, to stars so massive and so violent that they have never been directly observed, stars that may have rewritten the rules. The first stars were monsters. That is the scientific consensus. Confirmed through theoretical modeling and supported by the chemical evidence Webb is now collecting. The very first generation of stars, which astronomers call population 3 stars, formed from gas that contained only hydrogen and helium, the two lightest elements produced in the Big Bang. No carbon, no oxygen, no metals of any kind. That chemical purity had a dramatic consequence. Modern stars are partially regulated by the metals in their gas clouds. Those metals absorb radiation and allow the collapsing cloud to cool, which limits how massive any single star can grow before the heat from nuclear fusion pushes the remaining gas away. Remove the metals, and the gas cloud cannot cool efficiently. It keeps collapsing. It keeps accumulating mass. The result, according to models backed by the underlying physics of gas dynamics, was stars of extraordinary scale. Population 3 stars, likely ranged from 100 times the mass of our star to perhaps 1,000 times that mass, or even higher. Stars so hot they burned at temperatures exceeding 100,000 degrees at their surfaces, compared to around 10,000 degrees for a typical bright star today. At those sizes, they burn through their fuel at a ferocious rate. Where a star like our own might burn for 10 billion years, a population 3 giant would exhaust its fuel in just 2 to 3 million years. Then it would collapse. The largest among them would trigger pair instability supernovae, explosions so powerful they could leave no remnant at all, scattering the star's entire mass, now enriched with carbon, oxygen, nitrogen, and heavier elements forged in the stellar core across the surrounding space. One explosion from a single monster star could seed an entire region of the early universe, with the heavy elements needed for the next generation of stars to form, and for those stars to form faster and more efficiently. Then those second-generation stars could also produce more heavy elements and die, seeding the third generation, and so on. The cascade effect of this process may explain the chemical complexity Webb is detecting in early galaxies. The first few generations of population 3 stars could have turbocharged the chemical enrichment of their host galaxies in a fraction of the time our models assumed. Here is what makes this more than theory. Webb has not directly imaged a population 3 star. They likely no longer exist anywhere in the observable universe today. They burned too bright, too fast. But Webb has found tentative spectroscopic signatures in some early galaxies that suggest their light is being influenced by stellar populations with unusual chemical profiles. Profiles consistent with what you would expect from gas enriched by population 3 explosions. A team published a paper in 2023 identifying a gravitationally lensed arc of light from the very early universe that showed spectroscopic features their models could only explain with population 3 stellar activity. The finding is tagged as a strong candidate. A confirmed detection requires follow-up, and that follow-up is ongoing. But the signal is there. If population 3 stars were as massive and as numerous as models now suggest, they could have lit the cosmic dark ages ablaze far faster than previously assumed. They could have driven reionization ahead of schedule. They could have seeded the first galaxies with enough chemistry to explain what Webb is finding. And when those stars died, they may have left something behind. Something that would reshape every galaxy it touched. Something that grew faster than it should have, and sat waiting at the centers of the earliest structures in the universe. At the center of almost every large galaxy sits a supermassive black hole. Our own galaxy has one. It contains a mass equal to roughly 4 million stars like ours, compressed into a region smaller than our solar system. It is enormous by any human standard, and by the scale of the modern universe, it sits in the middle range of supermassive black holes. Webb found black holes in the early universe that make ours look modest. And the problem is not their size. The problem is when they got that big. Building a supermassive black hole takes time by the same logic as building a galaxy. A stellar mass black hole forms when a massive star dies and its core collapses under its own gravity. That black hole then grows by pulling in surrounding gas. As gas falls inward, it heats up, radiates enormous amounts of energy as a quasar or active galactic nucleus, and some fraction of that gas crosses the event horizon and adds to the black hole's mass. This process has a natural speed limit. The radiation produced by infalling gas pushes outward and resists more gas coming in. There is a maximum rate at which a black hole can feed, called the Eddington limit. If you start with a black hole of 10 solar masses, right after the Big Bang, and allow it to grow at the maximum possible rate continuously, for 1 billion years, you end up with a black hole of around 100 million solar masses. That is the theoretical ceiling under standard physics. Webb found black holes in galaxies from the first billion years, with masses exceeding 1 billion solar masses, some pushing toward 10 billion. These objects break the math. Even running at maximum feeding rate from the moment the first stars could have produced seed black holes, there is not enough time to grow them that large. The numbers come up short by a factor of 10 or more in some cases. Scientists proposed solutions. Maybe the seed black holes were much larger to start, formed directly from the collapse of massive gas clouds, rather than from dying stars. Direct collapse black holes, as they are called, could potentially start at masses of 10,000 to 100,000 solar masses, giving the growth process a substantial head start. Another proposal: maybe black holes in the early universe fed at rates above the Eddington limit, in short, extreme bursts, pulling in gas faster than the radiation pressure could push it away, particularly if the infalling gas came from specific directions that minimized the resistance. Webb has found evidence supporting the direct collapse scenario in at least some cases. Certain early black hole candidates show characteristics that match the spectral signatures expected from a very massive black hole accreting gas with no significant surrounding stellar population, suggesting the black hole formed before or alongside the galaxy, rather than growing gradually within it. A team working with Webb data published findings in 2004, showing a population of compact red objects in the early universe, now nicknamed little red dots, that appear to be black holes accreting gas at rates that challenge the Eddington limit. Hundreds of them, spread across the early universe, active and feeding in an era when they should barely have begun to form. The galaxy and the black hole grew together, it seems, feeding each other, accelerating each other, and the relationship between them may be far more intertwined than our models ever considered. That relationship is about to get stranger. Which came first? The galaxy or the black hole at its center? Astronomers have wrestled with this question for decades. In the modern universe, there is a striking relationship between the mass of a galaxy's central black hole and the mass of the galaxy's bulge, the dense central region of stars surrounding it. The two track each other with surprising precision across galaxies of vastly different sizes. That correlation implies a deep connection. The black hole and the galaxy did not just coexist. They shaped each other. But in what order and through what mechanism? The standard model offered a reasonable narrative. Galaxies formed first, pulling together gas and stars through gravity. As the central regions densified, gas fell inward and eventually seeded a black hole, which then grew as the galaxy matured. Webb found something that scrambles this sequence entirely. In the earliest cosmic epochs Webb can probe, the black holes appear overmassive relative to their host galaxies. The black hole is too big for the galaxy it sits in, by the standards of the relationship we observe in the modern universe. Instead of the black hole being a fraction of the galaxy's total mass, it represents a far larger share, sometimes approaching a few percent of the entire stellar mass of the galaxy. A team analyzing Webb data from ultra-early galaxies found black holes in some cases containing a mass more than 10% of their host galaxy's total stellar mass. In the modern universe, that ratio is typically less than 1%. The black hole had outpaced the galaxy around it. This flips the narrative. If the black hole was growing faster than the galaxy in the earliest phases, it was not a passenger riding inside a growing structure. It may have been a driver of that growth. The radiation and outflows produced by a feeding supermassive black hole can compress surrounding gas clouds, triggering bursts of star formation in regions that might otherwise have remained diffuse for longer. The black hole, by blasting energy outward, could have been sculpting the galaxy around it, forcing matter to collapse into stars on an accelerated timeline. This is the positive feedback loop that nobody anticipated. A growing black hole feeds. Feeding generates radiation. Radiation compresses gas. Compressed gas forms stars. Stars add mass and gravity. Gravity pulls in more gas. More gas feeds the black hole. The cycle accelerates. In the modern universe, this process eventually reverses. A black hole that grows large enough starts blowing gas completely out of the galaxy, shutting down star formation rather than triggering it. But in the earliest epochs, before that threshold was reached, the feedback may have been almost entirely constructive. Webb confirmed this picture in pieces. Measurements of star formation rates in galaxies hosting active early black holes showed elevated star production compared to galaxies without confirmed central black hole activity at similar redshifts. The effect is there in the data. What this means for cosmology runs deeper than the mechanics of individual galaxies. If the standard model assumed galaxies built themselves up through gradual mergers and accretion, and the actual early universe was instead driven by black hole feedback, accelerating the whole process, then every model based on the old assumption needs revision at a structural level. And if black holes were already this massive and this active in the first billion years, the structures they inhabited must have been assembling on a timeline that still has no satisfying explanation. That explanation may require something Webb found on an even larger scale, something that stretches across millions of light years and should have taken billions of years to form, something that was already there. Galaxy clusters are the largest gravitationally bound structures in the universe. A single cluster can contain hundreds or thousands of galaxies, all held together by mutual gravity, embedded in a vast cloud of superheated gas and anchored by an enormous reservoir of dark matter. The total mass of a major cluster can reach 1,000 trillion times the mass of our own star. They are the mountains of the cosmic landscape. Building one takes time. The Standard Model is clear about this. You start with small dark matter halos in the early universe. Those halos merge. Galaxies form inside them. Those galaxies drift together. More halos and galaxies pile on over billions of years. A fully assembled massive cluster, according to the standard timeline, should require at least several billion years of cosmic history to construct. Webb found clusters already assembling in the first billion years. Multiple groups working independently with Webb data identified what they are calling protoclusters, groups of galaxies in the early universe that are already gravitationally associated, already gathering mass, already showing signs of the organized structure that defines a mature cluster. Their existence at those redshifts sits outside the probability range of the Standard Model. One of the most striking finds involved a system at a redshift around 7.9, placing it at roughly 700 million years after the Big Bang. The system contains a central galaxy surrounded by multiple companion galaxies, all moving together, already showing evidence of interaction and coordinated motion. The total mass of the system, including estimated dark matter, approaches values that should take 3 to 4 billion years to accumulate. Think of it like arriving at a city that history says was founded 50 years ago, only to find skyscrapers, a functioning metro system, and neighborhoods with centuries-old architecture. The evidence of maturity is undeniable. The timeline says it cannot be. The implications reach beyond the clusters themselves. If large gravitational structures were assembling this early, it means the distribution of matter in the early universe was far lumpier, far more concentrated in certain regions than the Standard Model predicts. The model derives its predictions about lumpiness from the cosmic microwave background, which shows a universe almost perfectly smooth at the time of last scattering. The gap between that near-perfect smoothness and the concentrated structures Webb is finding in the first billion years is too large to explain with standard gravitational physics working alone on the predicted timescales. Something amplified the clustering, something made gravity more effective in certain regions, or made matter more concentrated, to begin with, or both. The theoretical proposals for what that something might be are pulling cosmology in directions that would have seemed fringe just a decade ago. One direction involves dark matter behaving differently than the cold, slow-moving, structureless substance the Standard Model assumes. Another involves physics from the very first moments after the Big Bang, specifically a period of exponential expansion called inflation, potentially leaving behind density fluctuations larger than standard inflation models predict. A third direction is even more unsettling. What if the large-scale structure of the universe, the web of filaments and voids that defines the distribution of matter across billions of light years, was already more advanced in the early universe than we thought? What if the cosmic web itself was sketched out earlier and more completely than the Standard Model allows? Webb looked at that question too, and the answer it found should rearrange how you picture the architecture of everything. The universe has a skeleton. Galaxies are not scattered randomly through space. They arrange themselves along vast filaments of gas and dark matter, like dewdrops clinging to a spider's web, stretched across billions of light years. Where filaments intersect, matter piles up into galaxy clusters and superclusters. Between the filaments, enormous voids stretch across hundreds of millions of light years, nearly empty of galaxies. This structure, called the cosmic web, is one of the most visually striking features of our universe at large scales, and our models predicted it would take billions of years to develop its full organized form. Gravity needed time to pull matter along the filaments, clear out the voids, and build up the dense nodes at intersection points. Webb found the cosmic web already sketched out in the early universe. Multiple observational programs using Webb targeted regions of the sky at redshifts between 5 and 10, corresponding to a time window from roughly 500 million to 1 billion years after the Big Bang. What they found was not the expected random scatter of early proto-galaxies. They found linear arrangements of galaxies, extended filamentary structures, coordinated distributions of matter that showed the characteristic pattern of the cosmic web at a scale and completeness that the standard model places several billion years later in cosmic history. One web-based survey found a filament of galaxies stretching across roughly 3 million light-years at a redshift of 6.6. Galaxies were strung along it at regular intervals, separated by voids. The spatial coherence of the structure was unmistakable. A filament of that scale and organization, by the standard model's mathematics, required around 2 to 3 billion years of gravitational evolution to form. It existed at less than 1 billion years. Scientists working on this dataset used the phrase remarkably advanced large-scale structure in their published analysis. That is the careful, measured language of researchers looking at data that does not fit and choosing their words precisely. For a listener, the more direct way to put it is this: the universe was organized far beyond what it had any right to be at that age. The web that should have taken billions of years to weave was already in place. This matters because the cosmic web is not a decorative feature of the universe. It is the architecture that determines where galaxies form, how they grow, how matter flows between them, and what the large-scale fate of the cosmos looks like. If that architecture assembled faster than we thought, then every model of galaxy evolution built on the standard timeline needs to be recalibrated from the ground up, and the source of that premature organization points toward the very earliest moments of cosmic history. The density fluctuations that seeded the cosmic web came from the Big Bang itself, imprinted during a period called inflation. If the web was more advanced earlier than predicted, then either inflation produced stronger density fluctuations than standard models assume, or something else was amplifying structure formation in the first billion years. One candidate for that amplification sits in the realm of what we call dark matter, the invisible substance that provides the gravitational backbone of every structure in the universe. Our model makes very specific predictions about how dark matter behaves. Webb is now providing the sharpest test those predictions have ever faced. And the test is returning results that are making some physicists deeply uncomfortable. Dark matter holds the universe together. It cannot be seen, felt, or touched. It produces no light and interacts with almost nothing. The only way we know it exists is through its gravitational influence on the things we can see. Galaxies rotate in ways that only make sense if they are embedded in vast halos of invisible mass. Galaxy clusters bend light far more powerfully than their visible matter alone could explain. The cosmic web itself traces the underlying skeleton of dark matter that pulled normal matter into its current arrangement. The standard model specifies what dark matter is like: cold, meaning it moves slowly compared to light; structureless, meaning it has no internal interactions or complex behavior; and smooth at small scales, meaning it does not spontaneously clump into dense concentrations below a certain size. This is the cold dark matter of the lambda cold dark matter model, and its behavior drives the predictions for how structure forms and evolves. Webb is now subjecting those predictions to scrutiny at scales and epochs they have never been tested at before, and several findings are creating friction. The first friction point involves the number of small dark matter halos. The standard model predicts an enormous number of small dark matter clumps throughout the universe, including in the vicinity of large galaxies. We should see a huge population of small satellite galaxies orbiting large ones, because dark matter halos attract gas and form galaxies. For decades, observations showed far fewer satellite galaxies than predicted, a problem known as the missing satellites problem. Proposed solutions existed, but they involved somewhat ad hoc adjustments. Webb is showing that the early universe also has fewer of the smaller structures than predicted, while simultaneously having more of the larger structures. The distribution of halo masses does not match the cold dark matter expectation. The universe looks like it built big structures faster and small structures more slowly than the model says it should. The second friction point involves the density profiles of dark matter halos. Cold dark matter predicts that the center of every dark matter halo should contain an extremely dense spike called a cusp. where the dark matter density rises sharply toward the center. Observations of galaxies, confirmed and extended by Webb, show cores that are more uniform in density, without the sharp central spike. This is the core cusp problem, known for years, but Webb's precision measurements are sharpening it into something harder to dismiss. A third friction point: warm dark matter models, where dark matter particles move faster and therefore suppress small-scale structure formation, fit some of Webb's observations better than cold dark matter does. Researchers have been running comparisons and finding that warm dark matter predictions align more closely with the galaxy size distributions and halo mass functions Webb is measuring in the early universe. This does not confirm warm dark matter. Science does not work through single observations, but it is a consistent signal appearing across multiple independent analyses. And it is forcing theorists to take seriously the possibility that the cold dark matter assumption, which has been the bedrock of structure formation physics for 30 years, may need revision. If dark matter behaves differently than assumed, every model built on the cold dark matter framework requires adjustment. The predicted timelines for structure formation, the expected distribution of galaxies at high redshift, the relationship between visible and invisible matter across cosmic history, all of it becomes negotiable. And the negotiation grows more urgent when you add what Webb has done to the most fundamental measurement in cosmology, a number called the Hubble constant. Because on that front, Webb did not reduce the tension. It made it significantly worse. There is a number at the heart of modern cosmology, a single value that describes how fast the universe is expanding. Every distance, every age estimate, every model of cosmic evolution depends on getting it right. Cosmologists call it the Hubble constant. For decades, there were two independent ways to measure it, and they disagreed. The disagreement was small enough that it could plausibly be blamed on measurement error. Then the measurements got more precise. The disagreement did not shrink. It grew. The first method involves the cosmic microwave background, the ancient light from the early universe. Scientists measure the precise pattern of temperature fluctuations in that light and use the standard model to predict what the Hubble constant must be today to produce those patterns. The answer that comes out of this analysis is around 67 kilometers per second per megaparsec. To put that in human terms, for every 3.2 million light-years of distance, the universe is expanding at roughly 67 kilometers per second. The second method is more direct. Scientists measure the distances to nearby galaxies using standard candles, objects whose true brightness is known, so the apparent brightness tells you the distance. The classic standard candle is a type of exploding star called a Type 1a supernova, which always explodes at nearly the same total brightness. Measure how bright it appears versus how bright it actually is, and you have the distance. Combine distance with the measured recession speed, and you get the local expansion rate. That measurement consistently returns a value around 73 kilometers per second per megaparsec, 67 versus 73, a gap of around 9%. In cosmology, a 9% disagreement between two independently measured fundamental constants of the universe is enormous. Either one or both measurements contain a systematic error nobody has found, or the standard model of cosmology is missing something real. Before Webb, some scientists hoped the discrepancy would dissolve once the measurements of the distance ladder, the chain of methods connecting nearby standard candles to distant galaxies, were made with greater precision. Webb was the tool to do that. Its infrared vision could measure Cepheid variable stars, the stars used as the first rung of the distance ladder, with far greater accuracy than Hubble could. Webb made those measurements. The 2023 analysis by a team led by Adam Rees, who won the Nobel Prize for discovering the universe's accelerating expansion, used Webb to recalibrate the Cepheid distance ladder with unprecedented precision. The results confirmed the local measurement of the Hubble constant remained near 73. The systematic errors the team could find and correct for did not bring the value down towards 67. The gap stayed open. Webb did not solve the Hubble tension. Webb confirmed it. Physicists now call it a crisis, a genuine conflict between two highly precise measurements of the same physical quantity using entirely independent methods. The statistical significance of the discrepancy is beyond 5 sigma. the threshold physicists use to call something a discovery. The chance that this discrepancy is a statistical fluke is less than 1 in a million. Something is wrong with the standard model. The question is what? Proposed solutions range from new forms of early dark energy that altered the universe's expansion rate in the first few 100,000 years, to modifications of gravity at cosmological scales, to entirely new physics that the standard model has no framework to accommodate. None of the proposed solutions are clean. All of them require adding new ingredients to the model that have no direct observational support yet. The Hubble tension is pulling cosmology toward territory where the familiar equations start to lose their grip. And the strangest part of this story is that the Hubble tension is only one of the cracks Webb has exposed. There are more, and they all point in the same direction. The standard model makes a specific prediction about how many massive galaxies should exist at any given point in cosmic history. The prediction is precise enough to be testable. You can survey a region of the sky, count the galaxies above a certain mass threshold at a given redshift, and compare the result to what the model says should be there. This comparison is called the galaxy stellar mass function, and it has been a core test of cosmological models for decades. Before Webb, surveys using Hubble and ground-based telescopes found rough agreement with predictions at moderate redshifts. There were hints of excess at high redshifts, but the samples were small and the error bars were large. Agreement within uncertainty was always achievable. Webb expanded the sample by an enormous factor and dramatically reduced the measurement uncertainties, and the comparison between observation and prediction became impossible to paper over. At redshifts above 7, corresponding to the first 800 million years of cosmic history, Webb finds significantly more massive galaxies than the standard model predicts. The excess is substantial. Some analyses find 3 to 10 times more massive galaxies than expected. In the most extreme high redshift bins, the observed numbers exceed the model predictions by factors that cannot be attributed to statistical fluctuation. A team of researchers published a paper in 2010-3 describing the situation in stark terms. They found that the abundance of massive galaxies at high redshift challenges the lambda cold dark matter model at a statistically significant level. Their language was measured. Their conclusion was not. To understand why an excess of galaxies matters so profoundly, consider what the prediction represents. The galaxy stellar mass function is derived from first principles of the standard model. It follows from how dark matter halos form, how gas collapses within them, how stars form from that gas, how supernovae and black hole activity regulate star formation, and how galaxies merge over time. Every link in that chain feeds into the final prediction. If the observed number of massive galaxies is 3 to 10 times higher than predicted, it means at least one link in that chain is fundamentally broken. Either dark matter halos were forming faster and more abundantly than the model predicts, or gas was converting into stars with greater efficiency than assumed, or feedback processes that should have limited star formation in early massive galaxies were weaker than models include, or some combination of all three. What makes this particularly challenging is that researchers have already tried to adjust the models. They have explored variations in star formation efficiency, tweaked feedback prescriptions, experimented with different dark matter models. None of these adjustments, applied individually or in combination, fully resolves the excess. The observed galaxy counts consistently outpace the adjusted predictions. One physicist, commenting publicly on the Webb results, used the word impossible to describe the abundance of certain early massive galaxies under the standard model. That word comes loaded with weight in physics. Using it means the speaker has checked the math multiple times and cannot find a way out within the existing framework. We are past the point of measurement uncertainty. The excess is real, confirmed across multiple independent surveys and analysis teams. The model is failing a fundamental test, which raises a question that would have seemed almost unthinkable a decade ago. What if the problem does not lie with our understanding of galaxies? What if it lies with something deeper? What if the framework that governs how matter behaves at cosmic scales, the equations of gravity and expansion that underpin the entire model, needs to be revised? That question is now being taken seriously by more physicists than at any point in the last 30 years. Every model in science carries an expiration date. The question is never whether it will eventually fail, but when. and on what evidence. For lambda cold dark matter, the evidence accumulating from Webb is not a single decisive blow. It is a pattern. Mature galaxies too early, massive black holes in the first billion years, galaxy clusters assembling ahead of schedule, the cosmic web organized beyond its predicted age. Too many massive galaxies at high redshift, the Hubble constant refusing to reconcile with itself, reionization completing faster than projected. Individually, each anomaly might find an explanation within a modified version of the standard model. Together, they form a consistent picture of a universe that organized itself faster, grew its structures more efficiently, and reached complexity earlier than the model allows. This pattern forces the question every physicist eventually dreads. Is the standard model a framework that needs adjustments, or a framework that needs replacement? The scientific community is not uniform in its answer. A majority of cosmologists still work within the standard model, applying corrections and extensions, trying to explain each anomaly with targeted modifications. This is reasonable science. Models should be adjusted before they are abandoned. The history of physics is full of models that survive challenges by incorporating new elements rather than being discarded. But a growing minority is asking a harder question. What if the modifications required are so numerous and so fundamental that the resulting model no longer resembles the original? At what point does patching a model become building a new one? One of the most discussed alternative frameworks involves modifying gravity itself. The standard model uses Einstein's general theory of relativity to describe how gravity shapes the large-scale structure of the universe. General relativity has passed every experimental test thrown at it within the solar system, and in the vicinity of dense objects like neutron stars and black holes. But those tests all occur at scales far smaller than the cosmic web. Modified gravity theories propose that Einstein's equations work perfectly at small scales, but require correction at cosmological distances. Some versions of modified gravity predict that structure formation at large scales would proceed faster than general relativity allows, which would help explain the advanced state of the early universe that Webb is documenting. These theories are not new. They have existed at the fringe of cosmology for decades. What is new is that Webb's data is giving them traction. Researchers who previously dismissed modified gravity as unnecessary are now running their simulations against modified gravity predictions and finding that the fit to Webb observations is, in several cases, closer than the standard model provides. A second alternative involves rethinking what happened in the earliest moments after the Big Bang. The standard inflationary period, the brief phase of exponential expansion that set up the density fluctuations seeding all subsequent structure, may have operated differently than assumed. If inflation produced a different spectrum of fluctuations, denser and more varied than the smooth, nearly scale-invariant pattern standard inflation predicts, those differences could explain the accelerated structure formation Webb observes. Testing this requires understanding inflation directly, something no current experiment can do. But the theoretical space is wide open, and Webb's anomalies are pushing physicists to explore corners of that space they had previously left uncharted. The deepest possibility, the one scientists discuss with the most caution, involves the Big Bang itself. The standard model treats the Big Bang as the absolute beginning, the moment from which all time and space flow. But some alternative cosmologies propose that the Big Bang was instead a transition, a bounce from a previous contracting phase, or a quantum tunneling event from an earlier state of existence. If the universe had a history before the Big Bang, even by a different set of rules, then the structures Webb is observing might carry imprints of that earlier phase, explaining why they appear more organized than a universe starting from scratch at the Big Bang should allow. That possibility sits at the outer edge of current physics. But the edge is closer than it used to be, and Webb keeps looking deeper. Every cosmologist keeps one image close. It is the cosmic microwave background map, the full sky photograph of the oldest light in the universe, captured with extraordinary precision by satellites over the past 30 years. It shows the universe as it looked 380,000 years after the Big Bang, the moment the hot plasma finally cooled enough for atoms to form, and light to travel freely for the first time. The map is almost perfectly uniform. The temperature of the light varies by only 1 part in 100,000 from one point in the sky to another. Those tiny variations are the seeds of all future structure. The the slightly denser regions that gravity would eventually amplify into galaxies, clusters, and the cosmic web. The standard model predicts the precise statistical distribution of those temperature variations. The pattern of their sizes and strengths is called the power spectrum, and it encodes information about the composition of the early universe, the amount of dark matter, the amount of normal matter, the rate of expansion, and the properties of inflation that generated the fluctuations in the first place. The match between the measured power spectrum and the standard model prediction is extraordinary. It is one of the greatest achievements in scientific history. The model predicts thousands of data points in the cosmic microwave background power spectrum with an accuracy better than 1%. Here is the problem. That same model, fitted so precisely to the cosmic microwave background, then makes predictions about the late universe, the universe we can observe directly with telescopes like Webb. Those predictions include the number of galaxy clusters at various masses, and redshifts, the large-scale distribution of matter, and the growth rate of cosmic structure over time. Those late universe predictions are where the trouble lives. A parameter called sigma-8 measures the amplitude of matter fluctuations in the late universe. The standard model, calibrated on the cosmic microwave background, predicts a specific value for sigma-8 today. Direct measurements of sigma-8 from galaxy surveys and weak gravitational lensing analyses consistently return a slightly lower value than predicted. The universe's matter distribution looks slightly smoother in reality than the model, trained on the earliest light, says it should. This sigma-8 tension, as it is called, has been present in the data for years. Webb is now tightening the measurements of matter clustering at high redshift in ways that will sharpen this test further. But the deeper issue is a philosophical one that runs through all of cosmology right now. The cosmic microwave background is a perfect fit to the standard model. The late universe observations show growing discrepancies. The model cannot be simultaneously perfectly right about the early universe and significantly wrong about the late universe, without something real happening in between, something the model does not account for. That something in between could be a new component of the universe, unknown physics kicking in after the cosmic microwave background era, or a modification to how gravity operates at late times. All three possibilities would require rebuilding significant portions of the standard model from new foundations. The baby photo is beautiful. It fits the model exactly. But what grew up from those early seeds looks different from what the model predicted, and the gap is becoming undeniable. The next step in this investigation leads deeper into the invisible half of the universe, the dark energy that drives its expansion, because Webb has found hints that even dark energy may be behaving differently than assumed. And if dark energy evolves, everything changes. Dark energy is the most abundant thing in the universe. It makes up around 68% of the total energy content of everything. And despite being everywhere, it is the least understood ingredient in the standard model. In the equations, it appears as a constant, a fixed energy density that fills space uniformly at all times and at all scales. This constant produces a repulsive effect that makes the expansion of the universe accelerate, driving galaxies apart at an ever-increasing rate. The model assigns dark energy a value and treats it as unchanging, a universal background hum that never rises or falls. This version of dark energy is called the cosmological constant, and it has been the standard assumption since observations of distant supernovae in the late 1990s first revealed the universe's accelerating expansion. The cosmological constant has always been theoretically uncomfortable. Quantum field theory, the framework that describes the behavior of all known particles and forces, predicts a vacuum energy density that should be enormous, perhaps the largest number in all of physics. The observed dark energy density is many orders of magnitude smaller than that prediction. Why the vacuum energy is so precisely suppressed, and why it takes the specific value needed to produce the gentle acceleration we observe, remains one of the deepest unsolved problems in physics. Webb has now added observational weight to that discomfort. A major analysis published in 2024, drawing on data from the Dark Energy Spectroscopic Instrument Survey and incorporating observations that Webb observations helped calibrate, found evidence that dark energy may be evolving over time. The signal is at the level of 2 to 3 sigma, below the 5 sigma threshold, for a firm discovery but consistent and present across multiple independent analyses. If dark energy evolves, the cosmological constant is wrong. Dark energy is something else entirely, something more dynamic, a field that changes its value as the universe ages. Physicists call this a quintessence field, and its existence would require adding a new dynamical component to the standard model, with its own properties, evolution, and interaction with the rest of the universe. Evolving dark energy would alter the entire history of the universe's expansion. A different expansion history changes the relationship between redshift and distance, which affects every distance measurement in cosmology. It alters the growth rate of structure at every epoch. It shifts the predicted values for the Hubble constant and sigma 8. An evolving dark energy could, in principle, explain the Hubble tension, though no specific model yet achieves this cleanly. The possibility also reframes the fate of the universe. A cosmological constant produces a specific long-term future: eternal acceleration, galaxies drifting apart, stars burning out, the cosmos cooling toward a dark, diffuse equilibrium. An evolving dark energy field could strengthen over time, eventually overpowering gravity so completely that it tears apart galaxies, then solar systems, then planets, then atoms, in a catastrophic end called the Big Rip. Or it could weaken and reverse, eventually causing the universe to contract in a big crunch. Webb's precise observations of distant galaxies at high redshift are feeding into the calibrations that will sharpen the dark energy measurement over the next several years. The telescope is already revealing subtle features in the distribution of galaxies that carry information about how dark energy has behaved across cosmic history. Each new data release tightens the constraints, and as the constraints tighten, the pressure on the cosmological constant grows. What Webb has assembled across all these findings is a portrait of a universe that is stranger, faster, and more complex than the model that has guided cosmology for 30 years. Every anomaly points in the same direction. The standard model is incomplete. What comes after it may be the most important question in science right now. And Webb is still watching. Some galaxies just stop. No explosion, no catastrophic collision. The stars simply stop forming. The galaxy goes quiet, burns through the stars it already has, and slowly fades from brilliant blue to a dim, aging red. Astronomers call this quenching, and in the modern universe it is understood, at least partially. A supermassive black hole reaches a critical mass, unleashes enough energy to blast the remaining gas out of the galaxy, and star formation shuts off. The galaxy retires. The standard model predicts quenching is a slow process. It requires a galaxy to first build up a massive black hole, which takes time, then for that black hole to enter an active phase energetic enough to drive out the fuel supply, which takes more time. Quenching massive galaxies in the modern universe typically unfolds over several 100 million to 1 billion years. Webb found a galaxy that had already finished quenching at a redshift of 4.6, placing it at roughly 1.4 billion years after the Big Bang. To be in a quenched state at that point, the galaxy had to have built itself up, grown a massive black hole, triggered the energy output needed to expel its gas, and completed the shutdown of star formation, all within 1.4 billion years. The standard model's timeline for that sequence runs to several billion years minimum. What Webb detected was the aftermath, a galaxy already populated entirely by old red stars, with no ongoing star formation, no detected cold gas reservoir, no signs of active construction. A finished product sitting in a universe that was barely a tenth of its current age. The research team that published this finding used spectroscopic analysis to confirm the galaxy's stellar population, old stars, chemically enriched, already past their productive phase. The spectral signatures were unambiguous. This matters beyond the individual galaxy. Quenching is a governor on galaxy growth. It sets an upper limit on how massive galaxies can become. If quenching was already happening this efficiently, this early, the early universe was cycling through galaxy formation and shutdown on a timeline compressed far beyond any model prediction. Galaxies were being built, growing, maturing, and shutting down in time windows that the standard model allocates to the construction phase alone. The feedback mechanism responsible must have been extraordinarily fast. A black hole reaching the critical energy output needed for full quenching in under 1 billion years requires either a very massive seed black hole to begin with, or feeding rates dramatically in excess of the Eddington limit, or both. Neither scenario fits comfortably within the Standard Model's parameter space. Webb subsequently found additional quenched galaxies at similarly high redshifts. Several candidates, some confirmed, each one representing a completed story in an era when the universe should still be writing the opening chapter. The cumulative picture is of an early universe cycling through galaxy life stages at a pace that seems almost frantic compared to the patient, gradual process the model describes. Galaxies were being born, growing massive, running their central engines, exhausting their fuel, and going quiet, all within timeframes that today require several times longer. Whatever physics drove this acceleration was not a minor tweak to the standard story. It was a fundamentally different regime of galaxy evolution operating in the early universe. And the strangest manifestation of that different regime was not a galaxy that stopped too soon. It was a galaxy that looked beautiful when it should have looked nothing at all. A spiral galaxy is one of the most organized structures in the universe. Those elegant sweeping arms, curving outward from a bright central bulge, represent billions of stars moving in coordinated orbits around a common center. They are not static features. They are density waves, patterns of compression rippling through the galactic disk, triggering star formation as gas passes through them. Maintaining that structure requires a galaxy to be rotationally stable, gravitationally settled, and old enough for the disk to have smoothed out and organized itself through countless orbital cycles. In our current era, spiral galaxies are common. About 70% of large galaxies show spiral structure. The Milky Way is one. Andromeda is one. They took billions of years to develop their characteristic forms. Webb found a spiral galaxy at a redshift of 2.36, placing it at around 2.8 billion years after the Big Bang. That finding alone pushed the confirmed existence of spiral structure earlier than expected. Then Webb found another at redshift 4.4, around 1.4 billion years after the Big Bang. Then, in a dataset from the JWST Advanced Deep Extragalactic Survey, a team identified what appears to be spiral arm structure in a galaxy at a redshift approaching 6, placing it at roughly 900 million years after the Big Bang. The galaxy carries the identifier Zhulong, named after a Chinese mythological dragon, because of its elongated, sinuous appearance in the Webb images. The visible structure extends across roughly 60,000 light-years, making it physically comparable in size to the Milky Way. And the morphology, the shape, the arms, the central concentration of light, all point unmistakably toward a spiral galaxy. At 900 million years after the Big Bang, standard models place the development of stable spiral structure in large galaxies at several billion years of cosmic age minimum. The disk needs time to form from the chaotic mergers of early proto-galaxies. It needs time to cool, flatten, and settle into organized rotation. The density waves that create spiral arms need a gravitationally stable disk to propagate through. None of those conditions should be present at 900 million years. Yet, there the arms are, resolved in Webb's infrared images with enough clarity to confirm they are a real structural feature of the galaxy, not an artifact of the imaging process, or a chance alignment of unrelated sources. The implications cut deep. Spiral structure is a tracer of dynamical maturity. Finding it this early means the disk formation process was faster and more efficient than models allow. It means the early universe was, in at least some locations, gravitationally calmer than expected, allowing fragile disk structures to form and survive, rather than being disrupted by the frequent mergers and collisions that early universe simulations predict. Or it means that spiral structure can form through a different mechanism in the early universe, one operating faster than the density wave instabilities that drive spiral arms today. Researchers are actively exploring this possibility, but no consensus explanation has emerged. What Webb has confirmed is that organized, rotationally symmetric large-scale galactic structure existed when the universe was less than 7% of its current age. The universe was building finished, elegant architecture in what should have been its rough construction phase. And what Webb found inside some of those early structures pushed the problem even further, because spiral arms were only the beginning of what should not have been there. Look at enough galaxy images, and you start noticing something in the center of many spirals. A bright, elongated bar of stars cutting through the core, with the spiral arms extending from the bar's ends rather than from the central bulge directly. These are called barred spiral galaxies, and about two-thirds of all spiral galaxies in the modern universe have them. The Milky Way is a barred spiral. A bar is not a passive structure. It forms through a specific gravitational instability in the disk of a galaxy. Stars orbiting the galactic center gradually drift into elongated orbits that align with each other, reinforcing a coherent bar-shaped density wave. The process requires the disk to be massive enough, rotationally stable enough, and old enough for these orbital resonances to develop and lock in. Theoretical models and computer simulations consistently predicted that bar formation requires a galactic disk with several billion years of evolution behind it. The standard expectation was that barred galaxies should be rare at redshifts above 1 and essentially absent at redshifts above 2. Webb found a confirmed barred spiral galaxy at a redshift of 3, corresponding to around 2 billion years after the Big Bang. Then, the dataset expanded. A systematic survey using Webb data identified a population of barred galaxies at redshifts between 1 and 3, with a fraction of the early galaxy population hosting bars significantly higher than pre-Webb models predicted. Then came a detection at redshift 4.4, corresponding to 1.4 billion years after the Big Bang. A bar, confirmed, clear in the imaging, spectroscopically verified as a coherent rotating structure at a time when the universe was barely 10% of its current age. The galaxy carrying this bar, informally called Sears 2112 by the team that identified it in the Cosmic Evolution Early Release Science Survey, is structurally comparable in its bar length and disk organization to barred spirals found in the nearby universe. The bar spans roughly 2,000 light-years. The disk surrounding it shows organized rotation. The overall morphology, if you extracted it from the image and placed it next to the Milky Way, would look familiar. Scientists working on the finding described it as deeply challenging to reconcile with standard formation timescales. The star-forming disk needed to produce the bar had to have been in place and rotationally stable for hundreds of millions of years before the bar could develop. That pushes the timeline for disk formation to an even earlier epoch. This compounds the spiral arm problem. Spirals form in stable disks. Bars form in stable disks that have had additional time to develop orbital resonances. Finding bars earlier than spirals were expected to exist means the disk maturity problem is even more severe than the spiral detections alone implied. Simulations run after the Webb bar detections have struggled to reproduce the observations. Some teams have found that by increasing the mass of dark matter halos in the early universe, they can accelerate bar formation to a degree, but not enough to fully account for bars at redshift 4. The models consistently land too late. The universe was building gravitationally stable, rotationally organized, structurally complex disks with internal bar features at a time when the standard model says proto-galaxy mergers should still be filling the sky with chaotic, irregular clumps of star-forming gas. Every confirmed bar in the early universe represents a gravitational system that solved an enormous organizational challenge ahead of schedule, and the chemical records locked inside those early galaxies reveal a similar impossibility in a completely different domain. Stars are element factories. Every atom heavier than helium in the universe was forged inside a star. Carbon and oxygen in the cores of medium-mass stars. Heavier elements like calcium and iron in the cores of massive stars. The heaviest elements, gold, platinum, uranium, in the violent collisions of neutron stars, or the explosive deaths of the most massive stellar objects. Each generation of stars enriches the surrounding gas with new elements when it dies, building up the chemical complexity of the universe, one stellar lifetime at a time. This process has a pace. It is governed by how fast stars form, how long they live, how they die, and how efficiently their expelled material mixes into the surrounding gas clouds. The metallicity of a galaxy, a measure of how enriched it is with elements heavier than helium, serves as a chemical clock. More metals means more generations of stars have lived and died within that galaxy. In the modern universe, metallicity scales predictably with galaxy mass and age. Massive, old galaxies are metal-rich. Young, low-mass galaxies are metal-poor. The relationship holds across billions of years of galaxy evolution and has been calibrated in enormous detail using ground-based surveys. Webb extended this calibration into the early universe, and the chemical clock started running at the wrong speed. Galaxies at redshifts between 5 and 10, corresponding to the first 1 billion years of cosmic history, show metallicity significantly higher than models predict for their age. Some galaxies in the first 500 million years already show oxygen abundances reaching 20 to 30% of the solar value. That level of chemical enrichment, according to stellar evolution models and the chemical enrichment rates they predict, requires multiple generations of massive stars to have formed, lived for a few million years, and died in explosive supernova, dispersing their enriched interiors. Multiple generations in 500 million years. Each generation of massive stars takes a few million years to live and die, but the gas needs time to collapse into the next generation, and the mixing of ejecta into the interstellar medium takes additional time. Running the full cycle several times within 500 million years requires star formation rates and gas cycling efficiencies at the high end of what is physically conceivable. One team analyzing a galaxy at redshift 8.7 found carbon and oxygen abundances that pushed their chemical evolution models to their absolute limits. The researchers stated plainly that reproducing these abundances within the available time required assuming star formation efficiencies significantly above what any observed galaxy in the modern universe displays. The problem sharpens further with nitrogen. Nitrogen is produced primarily in intermediate mass stars, which take longer to evolve and die than the massive stars responsible for oxygen. Finding elevated nitrogen in early galaxies therefore implies even longer chemical enrichment histories, further compressing an already impossible timeline. Webb detected nitrogen emission in galaxies at redshifts approaching 10. The signal was faint but real, confirmed through spectroscopy. Teams are still debating whether the nitrogen abundances require revising stellar nucleosynthesis models, star formation efficiency models, or both. What is clear is that the early universe's chemical record, like its structural record and its size record, tells a story of complexity arriving ahead of schedule, a story the standard model did not write. The volume of anomalies Webb has now documented, stacked across galaxy sizes, black hole masses, cluster formation, large-scale structure, reionization timing, metallicities, morphologies, and the Hubble constant, has reached a point where the scientific community can no longer treat them as isolated puzzles. They require a unified response. And that response is splitting cosmology into two camps with fundamentally different visions of where the field goes next. Science runs on statistics. A single anomalous result means little. 2 or 3 anomalies in the same direction begin to attract attention. A dozen consistent anomalies across independent datasets and analysis teams constitute a systematic problem. What Webb has produced over 3 years of observations is not a handful of puzzling results. It is a catalogue. Astronomers tracking the accumulating evidence from Webb have begun conducting what are called tension analyses, formal statistical assessments of how severely the observations conflict with the standard model predictions. These analyses take each anomaly, quantify its statistical significance, and ask whether the collection of tensions, considered together, is consistent with random measurement fluctuations or represents a coherent signal of model failure. The results are unambiguous. Considered individually, most Webb anomalies sit between 2 and 4 sigma, meaning they are unlikely to be flukes but not individually decisive. Considered together, across independent measurements, using different methods and targeting different physical phenomena, the combined statistical weight is overwhelming. A team published a formal tension analysis in late 2002-3 that combined the constraints from the Hubble tension, the sigma-8 tension, the excess of massive early galaxies, and the advanced state of large-scale structure. They found that the probability of the standard lambda cold dark matter model simultaneously satisfying all of these constraints was extremely small. Their analysis pointed clearly toward new physics. The statistical case is reinforced by a feature of the data that is easy to overlook. The anomalies are directional. Every excess points the same way. The early universe was more organized, more massive, more chemically enriched, and more structurally complex than the model predicts. There are no Webb discoveries suggesting the early universe was less developed than expected. The deviations are systematic, not random. Random measurement errors scatter in all directions. Systematic model failures produce consistent directional biases. The pattern in the Webb data is consistent with systematic model failure. This statistical picture is forcing a reckoning. Cosmologists who built careers on the standard model are now publicly acknowledging that something beyond minor adjustments is required. Papers using phrases like crisis in cosmology and paradigm tension have been published in leading journals by researchers at major institutions. Those phrases do not appear in mainstream scientific literature lightly. One researcher who has studied galaxy formation for 3 decades described the situation at a conference in 2204 as the most exciting and most unsettling period she had experienced in the field. Exciting because anomalies are where new physics hides. Unsettling because the anomalies are appearing in the foundations of the model, not at its edges. The response from the broader community is taking 2 forms. One group is working intensively to rescue the standard model through targeted modifications, new physics additions, and parameter adjustments. They argue that the model's core framework, cold dark matter, plus a cosmological constant, plus inflation, can survive if the right extensions are added. Their work is rigorous, ongoing, and genuinely productive. The other group is asking whether the extensions required have grown so numerous and so fundamental that continuity with the original model is an illusion. Whether what the field is actually building, piece by piece, through reluctant modifications, is an entirely new cosmology. Both groups are doing legitimate science, but only one of them is asking the question that opens the largest door in modern physics. What if the story of how the universe began needs to be told from the start? The Big Bang is the most tested idea in all of cosmology. The expansion of the universe, the existence and temperature of the cosmic microwave background, the abundance of hydrogen and helium forged in the first minutes, the large-scale structure of the cosmic web. All of these observations flow naturally from a universe that began in an extremely hot, dense state and has been expanding and cooling ever since. The evidence is deep and independent. The Big Bang framework is secure. What is less secure is the specific version of what preceded and immediately followed those first moments. The standard model incorporates a period of exponential expansion called inflation, lasting a tiny fraction of a second after the Big Bang, which smoothed out the universe and generated the density fluctuations seeding all future structure. Inflation is essential to the standard model. It solves several problems that the Big Bang alone cannot address. But inflation has never been directly detected. It is supported by indirect evidence and theoretical necessity. Webb's observations are now pointing towards specific features of the early universe that standard inflationary models struggle to predict. The advanced state of large-scale structure, the abundance of massive early galaxies, the compressed timeline for galaxy evolution. All of these could, in principle, reflect properties of inflation that differ from the standard prediction. Some versions of inflationary theory produce a power spectrum of density fluctuations with more power at small scales than the standard inflationary models predict. More power at small scales means more early structure formation, faster galaxy growth, and a more developed cosmic web at early times. A modified inflation model of this kind would move the predictions closer to what Webb observes. Physicists call this a tilted or running power spectrum. And while standard inflation produces a nearly scale-invariant spectrum, many inflationary models can produce variations. The question is whether the specific tilt required by Webb's observations is physically motivated or merely a post hoc adjustment. Beyond modifications to inflation, a more radical alternative exists. Bouncing cosmologies propose that the Big Bang was a transition point, a moment of minimum size and maximum density in a universe that had previously been contracting. Under this framework, the structures Webb observes might carry imprints from the contracting phase that preceded the Big Bang, explaining why they appear more organized than a universe starting from scratch would allow. Bouncing cosmologies are not mainstream. They face serious theoretical challenges, including difficulties preserving quantum coherence across the bounce, and questions about what physical process could halt a gravitational collapse and reverse it into expansion. But they are not ruled out by current observations, and several research groups are actively developing them. A third direction, perhaps the most mathematically adventurous, involves the concept of eternal inflation. In this framework, our observable universe is one bubble in an infinite, eternally inflating multiverse. Other bubbles may have different physical constants, different particle content, different histories. The structures Webb observes might reflect the specific properties of our bubble's inflation, which need not match the simplest predictions of the most minimal inflationary models. None of these alternatives currently make predictions specific enough to be directly tested against Webb data. But the tension Webb has generated is pushing theorists to develop them further, and future observations may eventually distinguish between them. The deepest question is deceptively simple. Did the universe begin at the Big Bang, or did something come before, something that left its fingerprints in the oldest structures Webb can see? The answer may depend on a type of evidence nobody has yet found, but Webb is already pointing toward where to look. Webb did not just find things that were too big and too old, it found things nobody had a category for. In the early deep field images, researchers cataloging sources came across a population of objects that looked different from anything in existing surveys. Compact, extremely red in color, and luminous enough to be detected at very high redshifts. They were not quite galaxies in any familiar sense. They were not quite active galactic nuclei in the traditional pattern. They were something else. The astronomical community gave them an informal name, little red dots. The color came from their spectral shape, dominated by emission in the red and infrared wavelengths, and their compactness suggested they were physically small, concentrated, and intensely energetic. Follow-up spectroscopy with Webb revealed that little red dots host actively accreting black holes in extraordinarily high concentrations relative to their surrounding stellar mass. In some cases, the black hole luminosity exceeds what the entire stellar population of the host galaxy would produce. The ratio of black hole mass to galaxy mass is, in several confirmed cases, far beyond anything observed in the modern universe. One confirmed little red dot, at a redshift around 5, has a central black hole estimated to contain a mass equivalent to several 100 million stars, while the surrounding galaxy contains perhaps a few 100 million solar masses and stars. The black hole outweighs the galaxy in stellar terms. In the modern universe, this ratio is reversed by a factor of several hundred. The existence of this population creates a new puzzle on top of the existing ones. If these objects represent a phase of galaxy evolution, where the central black hole dominates before the galaxy has built up its stellar mass, it supports the picture of black hole-led galaxy formation raised earlier. But the number density of little red dots, the sheer count of them per unit volume of the early universe, exceeds what models of black hole seed formation and growth predict by a substantial factor. Teams are actively debating what little red dots are. Some researchers favor a model in which they are extremely compact, dust-obscured galaxies where the red color comes from warm dust-absorbing starlight rather than from black hole activity. Others find the spectroscopic evidence for black hole accretion compelling enough that the dust model does not fully explain the observed emission line strengths. A third proposal is that little red dots represent a brief, extremely active phase that most massive galaxies pass through in the early universe. A phase so short-lived that it would be invisible in the modern universe, but appears prominently in Webb's high redshift samples, simply because Webb is seeing a much larger volume of early cosmic time. If that is correct, then virtually every massive galaxy today, including the Milky Way, passed through a little red dot phase in the first billion years. Our own galaxy may have once been one of these compact, black hole-dominated, intensely red objects, glowing in what was then a very young universe. The realization is startling, and it connects to an even broader question that Webb is now uniquely positioned to answer. How many of the early universe's surprises are not exotic exceptions, but instead the normal standard path that all galaxies walked? A path the standard model never predicted because nobody thought to look this early or this clearly. That question leads directly to the deepest implication of everything Webb has found. And it involves not just how galaxies formed, but what they tell us about our own position in the cosmos. The Milky Way is not special. That sounds dismissive, but it is one of the most important principles in modern astronomy, the Copernican principle, the idea that our location in the universe is typical, not privileged. We do not sit at the center of the galaxy. Our galaxy does not sit at a special point in the cosmos. Our era of cosmic history is not the pivot around which everything turns. Webb's discoveries are forcing a reconsideration of what typical actually means. If the early universe produced massive, structured, chemically complex galaxies far faster than the standard model predicts, then the formation history of every galaxy, including the one we inhabit, is different from what we assumed. The Milky Way did not build itself gradually over 13 billion years, through a slow, patient process of mergers and accretion in a universe where galaxy formation proceeded at the pace the model described. It formed in a universe that was operating in a fundamentally different mode in its earliest phases, a mode that was faster, more efficient, and more organized than the standard model captured. Whatever physical mechanisms drove the early formation of the galaxies Webb has detected, those same mechanisms were present in the patch of the universe that eventually produced the Milky Way. This reframes the origin story of our galaxy. If population 3 stars were as prolific and as massive as the early chemical evidence suggests, then the gas that would eventually form the Milky Way was being pre-enriched by their explosions within the first few 100 million years. If the cosmic web was already sketched out in the first billion years, then the filament that channeled gas toward the Milky Way's eventual location was already forming. If black hole feedback was accelerating galaxy construction across the early universe, then the Milky Way's own central black hole was part of that story from the beginning. Concretno Webb found something that reframes our galaxy's most important companion. The Andromeda Galaxy, our nearest major galactic neighbor, sits about 2.5 million light-years away. Models of the local group, the cluster of galaxies containing the Milky Way and Andromeda, predict that both formed gradually from smaller merging proto-galaxies over the past 12 billion years. If the formation efficiency of early galaxies was as high as Webb suggests, then structures like the local group may have assembled their basic mass distribution faster than models allow, with the major galaxies reaching substantial fractions of their current mass earlier in cosmic history. That affects estimates of when the Milky Way and Andromeda became dynamically distinct objects, when their satellite galaxies formed, and how their interaction history unfolded. It also affects the search for life. Planets require heavy elements. Heavy elements require stars to live and die. If heavy element enrichment of galaxies happened faster in the early universe, then the conditions for rocky planet formation, and by extension for life, arrived earlier in cosmic history than previously estimated. The universe may have been capable of producing Earth-like planets significantly earlier than our models predicted. This is speculative at present. The chain of reasoning from early galaxy metallicities to conditions for planetary habitability runs through many uncertain links, but Webb's chemical measurements of early galaxies are genuine data inputs to that chain, and they consistently point toward an earlier arrival of chemical complexity. The cosmos got complicated faster than we thought, and we are the product of that complexity. Our existence, in a real sense, traces back to the furious, compressed, improbably efficient first billion years that Webb is now finally revealing. Science changes slowly, and then suddenly. For most of its history, the standard model of cosmology accumulated evidence and passed tests. Anomalies appeared and were resolved. The framework held. But the history of physics also contains moments where the accumulating anomalies passed a threshold, and the framework could no longer contain them. The transition from Newtonian gravity to Einstein's general relativity was one such moment. Mercury's orbit had long shown a small deviation from Newtonian predictions. Other anomalies existed. Physicists had proposed patches and modifications. Then Einstein's framework arrived and explained everything Newtonian gravity had explained, plus the anomalies it could not, and the field moved on. Something structurally similar may be building in cosmology right now. The researchers calling most loudly for a new framework are not fringe voices. Several are among the most cited cosmologists in the world. Their papers appear in Nature, Science, and the Astrophysical Journal. They present at the field's most prestigious conferences, and their argument is straightforward. The modifications required to save the standard model have multiplied. Early dark energy was proposed to address the Hubble tension. Warm dark matter was proposed to address the missing satellites and core cusp problems. Enhanced star formation efficiency was proposed to address the excess of early massive galaxies. Modified galaxy feedback prescriptions were proposed to address early quenching. Each modification is motivated by specific observations. Each modification is individually defensible. But taken together, the modified model looks less like the original framework with refinements, and more like a new framework pretending to be the old one. The accumulated modifications are large enough to change the model's fundamental predictions across nearly every domain of galaxy formation and large-scale structure. At that point, the original model is not being saved. A replacement is being constructed in its shadow. Researchers explicitly calling for new cosmological frameworks are proposing several directions. One is a modified gravity cosmology, where the equations governing how gravity operates at cosmological scales differ from general relativity in ways that produce faster structure formation and resolve the Hubble tension without requiring dark energy adjustments. Theories of this type include modified Newtonian dynamics at cosmological scales and covariant tensor vector scalar gravity, a relativistic version of the same basic idea. Another direction questions the cold dark matter assumption at its root. Self-interacting dark matter models, where dark matter particles interact with each other through a new force, produce different halo density profiles and different small-scale structure formation rates. Fuzzy dark matter models, where dark matter consists of ultralight particles with wave-like behavior at galactic scales, suppress small-scale structure in ways that match several of Webb's observations more closely than cold dark matter. A third direction revisits the nature of inflation, proposing alternatives that generate primordial density fluctuations with different statistical properties. Some researchers have proposed that the Big Bang itself was preceded by a contracting phase that left an imprint on the subsequent structure formation. Others are exploring the idea that our observable universe formed as a black hole interior within a higher dimensional space, an idea that remains highly speculative but is gaining renewed interest as standard inflation shows signs of strain. The voices calling for new cosmology are growing more numerous and more confident, and they are being heard. Major funding agencies have begun supporting research programs explicitly aimed at testing alternatives to the standard model using Webb and future telescope data. The field is moving. The question is toward what? Webb is not the last word. It is the first sentence of a new chapter. The telescope's observations have generated enough anomalies and enough precise data to define the questions that the next generation of instruments must answer. And those instruments are already being built. The Nancy Grace Roman Space Telescope, scheduled for launch in the late 2020s, will conduct wide-field infrared surveys covering areas of sky hundreds of times larger than Webb's deep fields, at comparable depth and resolution. Where Webb has sampled small windows of the early universe with extraordinary precision, Roman will map enormous swaths of it. The statistical samples of early galaxies, early clusters, and high redshift large-scale structure that Webb has begun building will expand by factors of hundreds. That scale matters enormously for the questions Webb has raised. Many of Webb's tensions with the standard model involve the number density of rare objects, massive early galaxies, early clusters, quenched galaxies at high redshift. Establishing whether those number densities are truly anomalous requires large statistical samples that rule out the possibility that Webb's deep fields happen to sample an unusually overdense or unusual region of the early universe. Roman will provide those samples. The Vera C. Rubin Observatory in Chile, now completing commissioning, will conduct the Legacy Survey of Space and Time, a 10-year program mapping billions of galaxies across the visible sky. Its data will provide the most precise measurements yet of the late universe matter distribution, directly addressing the sigma-8 tension and providing independent constraints on dark energy evolution. It will also catch hundreds of thousands of Type 10 supernovae over its operational lifetime, sharpening the local measurement of the Hubble constant with an unprecedented statistical base. The Euclid Space Telescope, launched in 2010-3 and now returning science data, is conducting a wide-field survey of galaxy shapes and positions across a significant fraction of the sky. Its primary science goal is measuring the effect of dark energy on the large-scale structure of the universe through two techniques: weak gravitational lensing, the subtle distortion of galaxy shapes by intervening mass, and baryon acoustic oscillations, a standard ruler preserved in the distribution of galaxies from sound waves in the early universe. Euclid's measurements will directly test whether dark energy is a cosmological constant or an evolving field, potentially confirming or ruling out the 2 to 3 sigma signal from the 22004 analysis. On the ground, the extremely large telescope currently under construction in Chile will carry a mirror 39 meters across, roughly 4 times the diameter of the largest existing ground-based telescopes. Its spectroscopic capabilities will allow detailed analysis of individual stars and galaxies far beyond the local group, tracing chemical enrichment histories with precision impossible today. It will also conduct direct spectroscopy of high redshift galaxies identified by Webb, resolving features in their spectra that Webb's instruments cannot separate. Together, these facilities will transform the current catalogue of anomalies from qualitative tensions into quantitative constraints sharp enough to definitively distinguish between competing cosmological models. They will not merely confirm or deny the standard model, they will map the specific domain where the standard model fails and provide the data needed to build a replacement. The next decade of cosmology will be driven by the questions Webb raised, and the answers will determine whether the standard model survives in modified form or whether physics is standing at the threshold of a revolution as significant as the one Einstein triggered a century ago. Webb is still watching, and it keeps finding things nobody expected. Structure formation in the standard model is a two-sided process. Matter piles up along filaments and at cluster nodes, yes, but matter also empties out of the regions between those structures, creating voids, enormous stretches of space nearly devoid of galaxies. The standard model predicts that voids should grow gradually, expanding and emptying as the surrounding matter drains into the cosmic web, driven by gravity and the accelerating expansion of the universe. Voids in the modern universe reach sizes of a few 100 million light-years across. The largest confirmed void in the nearby universe, sometimes called the Boötes void, spans around 300 million light-years. Its existence pushed the edges of what the standard model comfortably allows, but it falls within the probability range, though barely. Webb, combined with data from surveys like the Sloan Digital Sky Survey and the Dark Energy Survey, has revealed that the distribution of voids and filaments in the large-scale structure is more extreme than standard model simulations predict. There are more large voids than expected. The filaments separating them are denser and more defined. The contrast between dense structures and empty regions is higher than the model produces. This enhanced contrast, called the matter power spectrum amplitude, at small scales, is directly related to the sigma-8 tension mentioned earlier, but it has a physical meaning beyond the statistical measure. It means the universe sorted its matter more aggressively into concentrated regions and empty voids than the model allows. A specific detection pushed this problem into sharp focus. Analyzing a combination of Webb observations and existing galaxy survey data, a team identified a region of the early universe, at a redshift around 1, that showed a void spanning an area equivalent to several billion light-years in co-moving scale. The void's size and depth, meaning how thoroughly evacuated of matter it appears, sits at the extreme tail of the distribution that lambda-cold dark matter simulations produce. Extreme tail does not mean impossible within the model, but when a measurement sits at the extreme tail of a model's predicted distribution, and other independent measurements are also sitting at the extreme tails of their respective distributions, and all of them point in the same direction, the cumulative probability of all of them being coincidental fluctuations becomes vanishingly small. That is the situation cosmology is in now. Each individual anomaly can be assigned a probability. It is low but finite. The combined probability of all anomalies occurring simultaneously in a universe governed by the standard model is approaching the level where it stretches credibility past its breaking point. Researchers modeling large-scale structure are now asking whether the void distribution requires new physics in the dark sector, the combined effect of dark matter and dark energy on structure formation. Specifically, whether dark energy varies in space as well as time, producing stronger repulsive effects in some regions and weaker in others, leading to the enhanced contrast between voids and filaments that observations reveal. A spatially varying dark energy would be a completely new ingredient in cosmology. Nothing in the standard model allows for it. It would require a field with spatial structure, meaning it has different values in different locations, which introduces enormous theoretical complexity and opens the door to interactions between dark energy and dark matter that the current model explicitly excludes. The void distribution is not the most glamorous of Webb's contributions to the crisis in cosmology. Voids are defined by absence, after all. But the absence of matter in regions that should be less empty than they are turns out to carry some of the clearest evidence that the universe organized itself by a different rulebook than the one we wrote. Everything discussed so far involves looking outward, at galaxies and structures billions of light years away. There is another kind of observation that works differently. Instead of looking at the sources of light, you look at the background itself, the cosmic microwave background, and you search for secondary signals imprinted on it by the structures light passed through on its way to our detectors. One such signal is called the kinetic Sunyaev-Zeldovich effect. When cosmic microwave background photons pass through a galaxy cluster, some of them scatter off the hot electrons in the cluster's gas. If the cluster is moving toward or away from us, this scattering introduces a tiny temperature shift in the photons, a distortion imprinted on the cosmic microwave background. By measuring these distortions across the sky and correlating them with galaxy positions from surveys, researchers can reconstruct the velocity field of matter across cosmic history. This technique provides an independent measurement of how fast matter has been moving and clustering, which directly reflects the growth rate of structure over time. And the growth rate of structure is one of the quantities where the standard model is showing strain. Recent analyses combining cosmic microwave background data from the Atacama Cosmology Telescope and Planck satellite with galaxy catalogs from large surveys found growth rate measurements that sit slightly below the standard model. Prediction: not dramatically below, but consistently below, and the significance has been growing as the measurements have improved. This is a different manifestation of the sigma-8 tension, seen now in the motion of matter rather than just its distribution. Matter is clustering, but slightly more slowly than the model predicts. Combined with Webb's finding that the early universe clustered faster than predicted, a picture emerges of a cosmos that front-loaded its structure formation, doing more in the early phases and less in the late phases than the standard timeline describes. This pattern has a striking theoretical interpretation. If dark energy is stronger at late times than the standard cosmological constant predicts, it would suppress late-time structure growth while leaving early-time structure growth unaffected. This aligns with the evidence for evolving dark energy, and with the Hubble tension, since a stronger late-time dark energy would also push the local expansion rate higher than the early universe calibration predicts. Taken together, these signals across completely independent observational methods, galaxy morphologies from Webb, void statistics from large surveys, cosmic microwave background secondary effects from microwave telescopes, tell a coherent story. The universe accelerated its structure formation early, then applied stronger brakes late. The standard model did not predict this shape of cosmic history. The data is convergent. Multiple probes using different physical principles, different telescopes, different analysis methods, arriving at compatible answers. In science, convergent evidence of this kind carries enormous weight. The standard model is struggling to accommodate it. And somewhere in the data Webb continues to produce, a signal even stranger than all of these is quietly sitting, waiting for the right analysis to pull it into focus. It involves not the distribution of matter or the expansion of space, but the fundamental symmetries of the cosmos, the question of whether the universe looks the same in every direction. It may not. Cosmology rests on a foundational assumption called the cosmological principle. The universe, on the largest scales, is homogeneous and isotropic. Homogeneous means it looks the same from every location. Isotropic means it looks the same in every direction. No preferred location, no preferred axis, no special direction that differs from any other. This assumption is so fundamental that it is embedded in the mathematical framework of the standard model at the deepest level. The equations that describe the universe's expansion, the Friedmann equations derived from general relativity, assume perfect isotropy. Without it, the standard model as currently formulated cannot function. Several analyses over the past decade have found hints that the cosmological principle may not hold perfectly at the scales we can observe. The most discussed of these is an anomaly in the cosmic microwave background called the hemispherical power asymmetry. One half of the sky shows slightly more temperature variation than the other half. This asymmetry was flagged by the Wilkinson Microwave Anisotropy Probe mission and later confirmed by Planck. Its statistical significance sits around 3 sigma. Its origin is unknown. Webb and associated large-scale surveys have added new data to this question. Studies of the distribution of galaxy spins, the direction in which galaxies rotate, have found a small but statistically significant tendency for galaxies on one side of the sky to spin in one direction more often than galaxies on the other side. If galaxies' spins were random, no such preference should appear. The signal is subtle, and its significance is debated, but multiple independent analyses using different galaxy catalogs have found consistent results. A separate analysis studied the dipole anisotropy in the distribution of radio galaxies and quasars across the sky. The standard model predicts a specific dipole signal from our motion through the universe. The observed dipole in distant radio sources appears larger than the prediction. The excess is around 3 sigma. If it reflects a true large-scale structure asymmetry rather than an artifact of our motion, it implies the universe has a preferred direction on scales of tens of billions of light-years. Webb's contribution here is indirect, but growing. As Webb builds up precise redshift measurements and positions for enormous numbers of early galaxies, those catalogs feed into isotropy tests that compare the distribution of galaxies in different directions on the sky at high redshift. Any angular asymmetry in the distribution, at a level that the standard model does not predict, would be a signal of large-scale anisotropy. Preliminary analyses exist. No definitive claim of cosmic anisotropy has been made, but the hints are there, spread across independent datasets and analysis teams, consistently pointing toward a universe that may not be perfectly symmetric on the largest observable scales. If the cosmological principle is violated even slightly, the Friedmann equations are not an exact description of the universe's expansion. Every cosmological measurement derived from those equations, every distance, every age estimate, every value of the Hubble constant measured through that framework, carries a systematic error that is currently unaccounted for. The implication is profound. A universe without perfect symmetry is a universe far more complex, far more structured at the deepest level than the standard model imagines. And a universe that complex may have an origin story equally more complex than the simple, elegant picture of a smooth beginning and a gradual, patient evolution that cosmology has carried for half a century. That picture is cracking. Webb is holding the instrument that is mapping the cracks in detail, and what it finds as it looks further and deeper may rewrite not just cosmology, but our most fundamental understanding of what it means for a universe to exist. Step back for a moment and look at the full picture. 3 years of Webb science have generated anomalies in galaxy formation, black hole growth, large-scale structure, chemical enrichment, galactic morphology, reionization timing, the Hubble constant, the matter-power spectrum, void statistics, and possibly cosmic isotropy. That is not a list of isolated puzzles. It is a coherent indictment of the standard model across nearly every domain it claims to describe. Physicists track the health of a theoretical framework by counting its free parameters and asking how many independent observations can be predicted without adjusting them. A good model makes specific predictions before the data arrives and confirms them afterward. The standard lambda-cold dark matter model has 6 free parameters that are set by the cosmic microwave background. With those 6 numbers fixed, it then makes predictions for everything else. The predictions are failing, not in one place, in many places, simultaneously. Researchers analyzing the cumulative tension have attempted to quantify it formally. Taking the Hubble tension alone at its measured statistical significance, the standard model is disfavored at more than 5 sigma. Adding the sigma 8 tension, independently measured through multiple methods, pushes the combined tension higher. Incorporating the excess of massive early galaxies, the advanced state of large-scale structure, and the evolving dark energy signal brings the cumulative statistical case to a level that would be called a discovery if it were pointing toward a new particle or a new astronomical object rather than toward a flaw in the prevailing model. The irony is that cosmology standards for claiming new physics are applied asymmetrically. A 5 sigma signal in particle physics declares a new particle. A 5 sigma tension in cosmological observations generates papers proposing patches and calling for more data. The field is understandably cautious. The stakes of abandoning a successful framework are high, but the caution is becoming harder to maintain as the anomalies accumulate. Several specific numbers crystallize the problem. The standard model predicts the universe should contain roughly one massive galaxy per unit volume at redshift 10, based on how structure forms from the cosmic microwave background initial conditions. Webb finds approximately 10 times that number. A factor of 10 is not a calibration error. It is a statement that a fundamental process in the model is wrong by an order of magnitude. At those redshifts, the Hubble constant discrepancy of 9% between early and late universe measurements has a direct physical interpretation. The universe is expanding roughly 9% faster locally than the early universe calibration predicts. Over the age of the universe, a 9% difference in expansion rate translates to a substantially different cosmic history. Either the universe is younger than the standard model calculates, or it underwent an episode of accelerated expansion that the model does not account for, or both. The matter-power spectrum amplitude discrepancy, the sigma-8 tension, implies that the universe today contains structures about 8% less concentrated than the standard model predicts from cosmic microwave background initial conditions. 8% in the amplitude of matter fluctuations, compounded over 13 billion years of structure formation, represents an enormous departure from predictions. Each of these numbers, taken individually, might be absorbed. Together, consistently pointing in the same direction, they represent a measurement of how far the standard model has drifted from reality. The drift is no longer small. The scientific community is in the uncomfortable position of knowing the model is wrong without yet knowing what the right one is. That position is where the most important physics happens, and Webb has placed cosmology squarely in the middle of it. If the standard model needs replacement, everything downstream of it gets revised. Start with the age of the universe. The current standard measurement places the age at 13.8 billion years, derived from the cosmic microwave background calibration, and the early universe Hubble constant. If the local Hubble constant measurement is correct, and the early universe measurement needs revision, the age of the universe could be as low as 12 to 13 billion years. If instead, the local measurement requires revision downward, and dark energy has been stronger in recent cosmic history, the calculated age could shift upward. The age matters. We have found stars in the Milky Way with estimated ages approaching 13 billion years. Some early analyses suggested ages even older than 13.8 billion years, which would be impossible under the standard cosmology. A revised age of the universe that is younger than the oldest stars would be catastrophic for cosmology. Current best estimates with realistic error bars keep the oldest stars within the allowed range, but the margins are uncomfortably slim, and a downward revision to the universe's age would eliminate the margin entirely. Distance measurements throughout cosmology depend on the Hubble constant. Redshift converts to distance, using the expansion history of the universe. If that expansion history differs from the standard model, every distance we have measured, using redshift as the ruler, shifts accordingly. The distances to galaxies, quasars, galaxy clusters, every object whose position in cosmic space and time we have mapped using the redshift distance relation, would require recalibration. The entire three-dimensional map of the universe would shift. This affects, among other things, our measurement of the size of the observable universe. The standard model places the edge of the observable universe at around 46 billion light-years in every direction, a sphere of roughly 93 billion light-years across. This figure comes directly from the expansion history. A different expansion history produces a different size. It also affects our calculation of the universe's fate. The long-term trajectory, whether the universe expands forever, eventually reverses, or tears itself apart in a big rip, depends on the precise values of dark matter density, dark energy density, and the expansion rate. If dark energy evolves, the fate is no longer fixed by the simple cosmological constant calculation. The universe's destiny becomes uncertain, in a deeper way than it was under the standard model. For astrobiology and the search for life, revised timelines for chemical enrichment change when the conditions for rocky planet formation were first met across the universe. If the earliest galaxies enriched their gas with heavy elements significantly faster than currently modeled, the first generation of Earth-like planets may have formed several 100 million to 1 billion years earlier than standard models allow. That pushes the potential origin of life, and intelligent life, further back in cosmic history. The implications for the search for extraterrestrial intelligence are subtle but real. If civilizations could have developed billions of years earlier than our models allowed, the universe has had more time to produce intelligence. The Fermi paradox, the question of why we have not detected signals from other civilizations despite the age and size of the universe, becomes even more acute under a cosmology that gives the universe more time and earlier chemical complexity to work with. Every calculation that builds on cosmological foundations gets revised when those foundations change. The history of science shows that such revisions, while disruptive, are ultimately productive. When Newton's mechanics gave way to Einstein's relativity, every calculation done in the old framework had to be redone. The new framework did them better and opened entirely new domains of physics in the process. What replaces the standard cosmological model will do the same. It will explain everything the standard model explains, plus the anomalies Webb and its successors are documenting. And it will open questions nobody has yet thought to ask. Webb is still operating, still pointing into the deep field, still collecting the ancient light of galaxies that formed when the universe was a fraction of its current age. Every new data release adds to the catalog. More high redshift galaxy confirmations, more precise chemical measurements of early stellar populations, more constraints on the distribution of dark matter halos at cosmic dawn, more barred spirals, more quenched galaxies, more little red dots, more objects that force theorists to reach deeper into their toolboxes for explanations. The telescope was designed to operate for 10 years, though its fuel efficiency during launch means it likely has enough propellant to function for 20 years or more. 2 decades of Webb data will transform cosmology in ways that are difficult to predict from here. In the same way that nobody in 2003, when Hubble was at its operational peak, could have predicted the specific discoveries that led to the current crisis. What is predictable is the direction Webb has established that the early universe organized itself faster than the standard model allows. It has shown that this is a systematic, statistically robust finding that persists across independent analyses. It has forced the scientific community to take seriously the possibility that the most successful model in the history of cosmology is incomplete in ways that are fundamental, not peripheral. The next generation of instruments will answer the specific questions Webb has sharpened. Roman will determine whether the excess of early massive galaxies is a statistical artifact of small survey volumes or a genuine abundance anomaly demanding new physics. Rubin will measure the matter-power spectrum with enough precision to definitively characterize the sigma-8 tension and determine whether it points to modified gravity, evolving dark energy, or a new dark matter property. Euclid will test whether dark energy has evolved over cosmic time, potentially confirming or ruling out the 2 to 3 sigma signal from 2200. The extremely large telescope will resolve stellar populations in early galaxies individually, turning chemical enrichment histories from statistical measurements into direct observations. And Webb itself will keep looking. The most distant galaxy confirmed today carries a redshift of 14.32. The theoretical limit of what Webb can detect pushes into the era of the very first stars. Population 3 stars, those theoretical monsters that may have lit the universe's darkest age, may yet leave a spectroscopic trace in the light of the most distant objects Webb can reach. Finding that trace would be one of the most significant astronomical discoveries in history, confirming a major piece of the missing physics the standard model needs. There is a particular image that captures where cosmology stands right now. Webb's deep field photographs show thousands of galaxies in a patch of sky so small you could cover it with a grain of sand held at arm's length. Each point of light is a galaxy containing hundreds of billions of stars. Many of those galaxies are so old and so distant that their light left before the Earth existed. Some of them left before any rocky planet could have formed anywhere in the universe, under the standard model's original timeline. They are all there, in the same tiny field of view, a library of universes within the universe. And scattered among them, the objects that should not be there, the massive early galaxies, the structured spirals, the chemically rich systems, the overgrown black holes, the anomalies that are quietly, persistently, scientifically dismantling a model that explained everything up until the moment a golden-eyed telescope looked deep enough to see what the model had missed. Cosmology is not broken. It is breaking open. And what pours out of that opening will rewrite the oldest story ever told, how everything that exists came to be. Webb is still watching.